Welcome to an introduction to chemistry, brought to you by Parkbench Tutors. For more information about Parkbench Tutors, look us up on Facebook or on parkbenchtutors.com. This is the last support tutorial relating to phase changes. Phase changes, remember, are about properties related to boiling point and freezing point. In other words, when we go between solid, liquid and gas. Colligative properties, these are those that depend on the concentration of particles and not on the type of particles. For example, the vapor pressure of an aqueous solution is lowered if you add more solute, because you need fewer molecules to maintain the liquid-vapor equilibrium. Freezing point then is lowered and boiling point is raised when you put a solute in. For water, we can express this in terms of the number of moles of solute per kilogram of solvent. Now remember, when we are using moles of solute and we are talking about a kilogram of solvent rather than a litre of solvent, then we are talking about molality, that's M-O-L-A-L-I-T-Y, and not molarity, right? So this is molality. So for molecules that don't dissociate, a 1m solution freezes at minus 1.86 degrees Celsius and it boils at 100.51 degrees Celsius. In other words, a 1m solution has lowered the freezing point and it's raised the boiling point. If you have a 2m solution, then you double the amount that the freezing point is lowered by, so it freezes at minus 3.72 degrees Celsius and it will boil at 101.02 degrees Celsius. Now, what happens when you have molecules that are ionized? In other words, they are completely dissociated. For example, hydrogen chloride and sodium chloride. If you have a 1m solution, then each has got two particles as ions, hydrogen ion and chlorine ion in one case, and sodium ion and chloride ion in the other case. So the boiling point for a 1m solution will be 101.02 and the freezing point will be minus 3.72. That's in degrees Celsius. What about calcium chloride solution? Well, there we would have the freezing point of minus 5.58 degrees Celsius. Calcium chloride, remember, it's CaCl2. And its boiling point would be 101.53 degrees Celsius. A couple of problems that you might come across which are related to this. Urea behaves as a molecular non-ionizing compound, so if we have 1.5 grams dissolved in 105 grams of water, it produces a solution boiling at 100.12 degrees Celsius. Can we find the molecular mass of urea from this? Well, we ought to be able to. Let's first start by saying, well, what will be the amount of urea in 1,000 grams of water? So we're going to take 1.5 over 105, and that will be equal to x over 1,000, where x, of course, is the amount of urea. So x will work out to 14.28 grams in 1,000 grams of water. Remember, I'm trying to find the molality here. So each mole produces a change in boiling point of 0.51, and we've got a change in boiling point of 0.12 produced by 14.28 grams. So if I take 0.12 divided by 0.51, I can realize that I've got a 0.235 m solution. Okay, so 14.28 divided by 0.235 times x over 1, and x will equal 60.8 grams per mole. So the molecular mass of urea then is 60.8. Let's have another worked example for you. 50 grams of glucose, which has got a molar mass of 180, and 50 grams of sucrose, has a molar mass of 342. They're each dissolved in 1,000 grams of water. So which has got the higher boiling point and which has got the lower freezing point? Well, since both of them are in 1,000 grams of water, the first thing to find is the molality. So for glucose, 50 over 180 is equal to 0.278 molar. And for sucrose, 50 over 342 is equal to 0.146 molar. So we know that a 1m solution produces a rise in boiling point of 0.51 degrees Celsius. So 0.278 times 0.51 will give a 0.14 rise for glucose, so the glucose would have a boiling point of 100.14, and sucrose it would be 0.146 times 0.51, which will be a rise of 0.07, so the boiling point would be 100.07 for sucrose. Well, you can see that the highest boiling point it would be for the glucose, and you could see, we can relate that to the fact that the glucose solution was 0.278 m, so its molality was higher than that for the sucrose. A similar thing would happen, of course, for freezing point. The glucose would freeze at 0.52 degrees Celsius, and the sucrose for minus 0.52, and for the sucrose it will be minus 0.27 degrees Celsius. So why do we get these differences? Well, remember, in sugar you've got 1 mole of particles, but in hydrogen chloride that has 2 moles of particles, 1 mole of hydrogen ions, 1 mole of chloride ions. In calcium chloride there are 3 moles of particles, 1 mole of calcium ions, 2 moles of chloride ions. And you can see that a similar relationship would exist for boiling point, so a mole of sugar particles would lower the freezing point by minus 1.86 because it's only 1 mole of particles, but in calcium chloride's case, where there are 3 moles of particles, then you would lower it by 3 times 1.86, so you would have a freezing point of minus 5.58. And finally some work on crystals, which show repeated pattern structures, and the plane surfaces make distinct angles with each other. The smallest part of the lattice that shows the repeated pattern is called the unit cell. If you have a substance that in its crystalline form holds a distinct amount or definite amount of water, then we call its crystal structure a hydrate, and if you heat it we have an anhydrous powder, that means without water. So some hydrated crystals lose water when exposed to air, those are known as efflorescent crystals, and some gain water, they're called deliquescent or hygroscopic. So that completes our work on phase changes, brought to you by Parkbench Tutors, narrated by David Hopcroft. Thank you for watching and listening. We wish you success in your studies. For more information about Parkbench Tutors, find us on Facebook or contact us at parkbenchtutors.com.